Welcome to this explainer on knowledge and reasoning, where we're going to explore the incredibly fascinating evolution of how machines actually learn to think. We'll be tracing the journey of artificial intelligence as it moves from rigid, unbending rules all the way to handling the messy, incredibly complex reality of our everyday world. So if you've ever wondered how a machine goes from just knowing simple facts to making highly nuanced decisions, you are absolutely in the right place. Let's dive in.
Here is our agenda for today. First, we'll meet the knowledge-based agent. Then, cover the rules of logic. Third, navigating an uncertain world. Fourth, the magic of fuzzy logic. And finally, designing real-world AI solutions.
All right, Section 1. Let's meet the knowledge-based agent, basically the hero of our explainer.
So what exactly is this agent? Well, at its core, a knowledge-based agent is definitely not just some glorified calculator. It's an entity that actively applies represented, stored knowledge to solve whatever problem we throw at it. Think of it as a system that holds a rich database of facts about its environment, and it's constantly querying that database to figure out its very next move. To really put this agent to the test, computer scientists love to mentally drop it into something called the WUMPUS world. It's this classic simulated grid environment. Picture a dark maze where the agent is encountering bottomless pits, piles of gold, and yeah, a monster called the WUMPUS. With no map and only basic local sensors, it has to use propositional logic, literally comparing what it's sensing right now to what it already knows, just to reason step by step and survive.
But how does it actually reason through a life-or-death problem like that? Let's move to Section 2, the rules of logic, specifically propositional and first-order logic.
When we get into first-order logic, or FOL, the absolute key is inference. How does the agent connect the dots? Well, step one is forward chaining. That's taking known data and inferring entirely new facts from it, basically pushing forward to a logical conclusion. Step two, backward chaining, works in reverse. You start with a specific goal and work backward through your knowledge base to find the facts that actually support it.
This leads us right into how we apply all this in knowledge engineering. Obviously, the AI relies on strict syntax and semantic structures to give everything meaning. Then it uses these really cool tools like unification, which is essentially playing a massive game of pattern matching to make different expressions look identical, and resolution, which is a powerful rule that systematically whittles down all the possibilities until a concrete proof finally emerges.
Now, our agent is absolutely killer at this kind of black and white logic. But it kind of forces us to pause and ask a pretty massive question. How does a machine cope when the real world is messy, totally unpredictable, and completely lacking in absolute truths?
Which brings us to Section 3, navigating an uncertain world, dealing with the unknown.
When things get uncertain, definitive facts just don't cut it anymore, so we need specialized methods. Instead of binary rules, we analyze inferences using belief networks, which beautifully map out probabilities and relationships. We also bring in frameworks like the Markov decision process. This allows an agent to make a whole sequence of decisions in environments where the outcomes are partly random and only partly under its control. It is a literal game changer for artificial reasoning.
All right, let's jump to Section 4, the magic of fuzzy logic, moving beyond binary true and false.
Think about the direct contrast between these two concepts. Classical sets have strictly black and white boundaries. Something is either entirely inside the set or it's out, true or false. But real life isn't like that, right? Fuzzy set theory introduces shades of gray. By using something called a membership function, a variable can actually have a degree of truth, say 70% true. This is revolutionary for handling real-world concepts like temperature or speed, because those things rarely exist in simple binary states.
And you know, this exact same evolution applies to relations too. When a machine tries to understand how two fuzzy concepts relate to each other, standard math kind of breaks down. So instead, it relies on complex mechanics like fuzzy max-min and max product composition. These are basically the mathematical gears that allow the AI to combine different fuzzy rules while perfectly preserving those crucial shades of gray.
So how does this all come together? It forms a complete fuzzy system pipeline. Step one is fuzzification. That's taking crisp, real-world inputs, like a sensor reading of exactly 72 degrees, and turning them into fuzzy values. Step 2 applies the fuzzy extension principle, filtering those fuzzy values right through the system's rule base. And finally, Step 3 uses defuzzification methods to translate that fuzzy conclusion back into a crisp, totally usable output. Something like telling a motor, hey, spin at exactly 400 RPMs.
Finally, Section 5, Designing Real-World AI Solutions. Let's talk practical applications and risk validation.
Because at the end of the day, the ultimate goal of all this knowledge and reasoning isn't just theory. The goal is to practically design fuzzy controllers. We're talking about the actual brains inside smart washing machines, self-driving cars, and industrial robotics. We want to develop sustainable solutions for incredibly complex problems. But, and this is absolutely crucial, we must rigorously verify and validate those designs. We have to identify any potential risks or impacts that might be hidden deep within the rule base we've just created.
Which leaves us with a pretty massive, provocative thought for you to ponder today. We've seen how beautifully machines can evolve from operating on rigid black and white logic to successfully navigating the gray areas of fuzzy real-world controllers. But as they take on more and more responsibility in these deeply uncertain environments, how do we successfully identify and confidently validate the real-world risks they might pose in our daily lives? The math behind all this is brilliant for sure, but the human oversight required to govern that math, that is the next great frontier. Thank you so much for joining me for this explainer.